Okay, here we've got a Stella window. Stella is symbolic systems simulation software made by a company called High Performance Systems. That's their website is HPS Inc. This software is available to students, I think at about $110 now for a fully functional version. You can get a download for free, but the download won't allow you to save your work. It'll do everything except save. So you can play someone else's model, but you just can't save your own work. Okay, let's try building our little hydraulic head model. I'm going to first go up and get this little icon here and pull it down. It's called a stock, represented by this little square, and we will type the name that I've chosen, which is head for hydraulic head there. A stock is any quantity that you could measure. In this case, the volume of water in the tank or the head, which would be proportionate to the volume. Conveniently, we're going to actually flow. That's what this operator is called. We're going to flow the stock out. We're going to flow it into an infinite sink, and that's represented by this little cloud here. I think Stella was designed to appeal to sophomores. And we'll just call this outflow. And so now we've got a stock and we've got a flow from that stock. The way Stella works is it simulates a process at intervals of time that you specify. And so let's go right now and go to the run specs, as they're called, and tell Stella how long we want to simulate this process and at what interval. The default is always 0 to 12 at 0.25 increment others. I don't want to use that. I'm going to use hours for my units of time, and I'm going to run this thing. Let's run it 24 hours. What do you say? And let's make our increment here 1 hour. So what we're going to do is simulate a process at 1 hour increments, and we'll be able to watch this flow change over this 24-hour period according to whatever rule we specify here in our outflow. In order to specify the actual relationships, you've got to get away from this conceptual view, this global view here, and go to this little chi-square symbol, which is the functional view, and then we got question marks in our two operators here, both our stock and our flow. So when we open up the head operator by double-clicking on it, this stock, it wants to know what's the initial value of this stock. Well, let's make it 20. Let's make it 20 meters. So we'll say that this represents 20 meters of head in this 1 meter by 1 meter square tank. What about outflow? Well, we might simply have it be a constant, although we might decide that doesn't make good sense physics-wise. But let's just set outflow at 1/10 of a unit per time step. And what kind of step? Well, what would that be? That would be 1/10. That would be in cubic meters. Right, because it's 1 meter by 1 meter by meters deep, so we'll just say, meters cubed per hour is our discharge rate. So we'll do okay on that. So now we've actually got a model, I think, that will run, and we can go down and get this little icon here, this little run controller, and we can run the model, and it ran, but we don't see any outputs. So you got to use one of these output functions in order to see what happened. And of course, I'm kind of a graphically oriented person, so I like graphs. So I'll use the graph icon, double click on it, and we're asked, what do we want to graph? Well, we want to graph head, and I want to I want to actually choose the range of head that I want to see. So I'm going to click over here where this little arrow is after I've selected head and show limits on it. And instead of letting it go from 1760 to 20, I want it to go from 0 to 24. Okay, so now we've got something we can actually see. Let's run our model again and see what happens. Well, there's our discharge. There's our head. It went down from the 20 that we started with to how much? Well, actually, another neat little feature about the later editions of Stella is that you can actually click down and move your cursor and read the values of the variables. So at 24 hours, we've still got 18 meters of head in this tank. We can probably get a little more resolution by clicking on the variable and then going down to a precision of tenths instead of 0. And now we can see that sure enough we had 17.6. Okay, well, that's fine, but probably that's not the way water flows out of a tank. Water probably flows out of a tank as an exponential decay process. And by that I mean that the rate at which this variable changes is proportionate to its magnitude. The constant of proportionality we call the exponential rate constant. So the way to write that down is to say, okay, let's say that it's not a tenth of a unit per hour. It's 1/10 times the value of the variable. So 10% of head per hour is going to be now lost or discharged. Well, we're getting a complaint from Stella. That's not an input. Well, it's not an input because I haven't made my little connector between this variable and this variable. And I do that by pulling that little arrow icon down and dragging it from the one variable to the other. And now when I double click on outflow and close the window, it should be happy. So let's see what the graph looks like when I run it now. Well, that looks a little bit more like an exponential decay. So the rate at which head is lost from the tank is proportionate at every moment to the amount of head in the tank at that moment. And so, since head is being lost, the curve becomes ever flatter, ever more gradually approaching the 0 point, which will, if we ran the simulation to infinity, time infinity, then the value of head would go to 0. Okay, well, exponential decay processes are linearized if one takes the logarithm. So one thing we might do is use another icon. This is called a converter. It's also a constant and it's also a variable. The name I don't think fits very well, and we'll call this log head. And what I want to do is connect head to that variable, and I want to transform the value of head to its logarithm. And we can go to the built-ins or the intrinsic functions in Stella and pick up the natural log, which is right there, log to the base n, or to the base e, log n, the natural log, the Napierian logarithm. And what we want to take the logarithm of is head. So I put my cursor between the two little parens, and I'll go up and click here, and that gives us the logarithm of head. Now let's take a look at our graph. We'll go ahead and add that variable to the variable that's already there, head, and I'll just let this one free float because I don't know what range the logarithm is going to have. And now when I run my model, I see that the logarithm, in fact, is a linear function of time, and that makes it a logarithmic process. Well, how do you get any environmental sensitivity in it? Maybe this fluid that we've got in this tank really isn't water. Maybe it's molasses. Maybe it's something that gets more dense as it gets cold. So how about we put temperature into our model? So we'll just call this TA for ambient temperature, and we'll connect it to our outflow, and we'll set temperature to be a constant, at least first, 25 degrees, let's say. Now, how would we incorporate the effect of temperature in the flow rate? Well, maybe all it does is alter our rate constant in some exponential fashion. And so we represent that by saying we're going to multiply that whole works by e raised to the power 0.07 times ambient temperature. I chose the 0.07, folks, because it turns out that that's the coefficient that corresponds with a Q10 of 2, if you know what a Q10 is. The rate is going to double for every 10-degree change in TA. So now let's have a look. Whoa! Greatly speeded up our rate. So at high temperature, well, how do I know this was high? I know it's high because when I take a look at this outflow function, I can see that if TA is 0 degrees, 0 times anything is still 0, and e to the 0 is 1. And so the function, the way I had it before I put temperature in, is actually the response at 0 degrees. And to prove that to you, let me put 0 in for temperature. And when I do and run the model, you'll see that we get exactly the same result that we got before. And there it is again. So that's the way Stella works, and that's only a very few features of Stella. There is one more feature that I'm going to splurge and show you here. I'm going to say, okay, let's let temperature not be a constant. Let's let temperature vary as a function of time. So I'll just type in the word time, because time is an intrinsic, a proprietary variable in Stella. So Stella knows what time is, and I'm going to make that become a graphical function. And when I do that, it gives me it gives me zeros here. In other words, it takes the constant value of temperature that I had and propagates that for all 24 hours. I'm going to make 25 data points. So I'll have 1 per hour. And now I can either enter the data manually, 20 degrees at time 0 and 30 degrees at time 1, or if I'm lazy, I can go over and put my cursor down here in the window and just drag in the values. So that makes it very convenient to put variable values of some variable into Stella. Another way to get these values in is by cutting and pasting from a spreadsheet like Excel. That's a bit of a tedious process. Okay, let's try running our model now with variable temperature just to see what happens. Head can't be evaluated because of division by 0 or a value that has become too large to represent. The simulation will be terminated. That's a frequent result in when you're not careful about your math. And I'm not sure just what we did there. Let me pause a moment and try to collect. Okay, I'm back. I, as we say, took a little station break to figure out what was going on, and what was going on was that head was getting so close to 0 that we ended up trying to take the log of minus infinity there. So we can fix that in a couple of ways. One thing is I wasn't noticing that my TA scale by default was going all the way up to 100 degrees, so by just making the temperature a little bit lower, we can probably manage the situation. Let's try running it now and see what happens. So now we're exponentially nearly decaying, but not so close to 0. There's another way to fix this kind of problem, and that is to go into this log function and sort of prevent it from ever happening by putting in a maximum in other words, take the logarithm instead of head, take the logarithm of maximum of two quantities, one of them being head and the other one being some number that's very close to 0, but not nearly as close to 0 as head got. So now we won't, or we shouldn't have the error. We should get a log that's approaching minus a large number, but not minus infinity. Let's see what happens when we try that. It shouldn't affect us on that, but when we change TA to the higher values that we had before, let's see what happens. So we're protected. The head dropped to nearly 0, but the logarithm of head never went below minus 15. It went to about minus 14 and stopped. So that's the way we often work in Stella. This was a good accident because it shows you reality. And if we don't like what we did, we can always use another little sophomoric tool, a stick of dynamite, and just blow our stuff away. By the way, Stella has no undo, so you got to be really careful with that dynamite. You need to save your work frequently and be careful with the dynamite.